All right, so we're starting, as I said, in Chapter 2 with rates of change and limits. We're going to talk about, real quickly, average and instantaneous speed. Average speed is something that you've known about since junior high, maybe earlier than that even. So the average speed of a moving object during an interval of time is found by dividing the distance traveled by the elapsed time, right? You drive 100 miles in 2 hours, you're traveling at an average speed of 50 miles an hour. That's pretty simple. The difference between calculus and those sort of junior high ideas is, well, we're going to be interested in finding the instantaneous speed. Hey. Oh.
And she's like, I can't turn it on.
Can she not reach the button?
No, Miss Salinas? I don't think so.
Oh, it's in her room?
Yeah.
I'd pay money to watch her trying to reach it.
Exactly. Yeah, it would be both.
Here, take the bag.
Thank you.
You're welcome. Sorry about that.
No, it was my fault. I was gonna come Monday and I completely forgot.
Gotcha. All right. So the average speed, or the average rate of change in the distance the object is covered from time ta to t is equal to b, is going to be f of b minus f of a over b minus a. You guys have seen something like that, right? What does that, or what is it that you've seen that's like that? It's actually two different things. Slope, yeah, this is a slope. You're like, okay, that's cool. What else? Did you do something last year? Yeah, the average rate of change. Okay, and actually that's fairly new. That's not something that pre-cal used to do. So that's your average rate of change. So let's take a look at this problem. A rock falls from the top of a tall cliff. What is its average speed? Hang on a second. Come on, seriously. Find the Wacom tablet. Technology is great when it works. If it doesn't, it sucks. All right, well, I'll do something else. A rock falls from the top of a tall cliff. What is its average speed during its first 2 seconds of fall? What is the instantaneous speed of the rock at t is equal to 2? Estimate your answer graphically and numerically, then confirm algebraically. I'm going to give you one more chance. God bless you. There we go. All right. Well, part of it is you need to figure out, you need to know an equation for how far is this rock going to fall in t seconds. So from physics, you may remember, or you may not, and that's quite all right, that the distance it's going to fall in terms of feet is 16t squared feet. So if we do the average speed is going to be equal to y at 2 minus y at 0 over 2 minus 0. So that'll be 16 times 2 squared minus 16 times 0 squared over 2 minus 0. Hey,
Great day.
You too. Told you he was coming. Mr. Vargas threw me under the bus. All right. So 16 times 4 is 64. Minus nothing is going to be 64 over 2. This is 32 feet per second. Now, a different question is, well, what's the instantaneous speed of the rocket t is equal to 2? Well, if we tried to find the instantaneous by doing y of 2 minus y of 2 over 2 minus 2, what do we end up with? Really? Well, you end up with 0 in the numerator and 0 in the denominator. That's bad. Okay, that is something we'll talk about later. It's called an indeterminate form. 0 over 0 doesn't make any sense at all, because normally if 0 is on top of a non-zero number, what do you have? 0. And if you have a non-zero number divided by 0, what's that? Undefined. Okay, so which is it? Is it 0 or is it undefined? It turns out in this case, it's neither of those. So how are we going to do this? If you've got your calculator, pull that puppy out. All right, so what I'm going to do is go into y equals and say 16x squared. And actually, I kind of want the whole thing, don't I? Well, let's go back to this for just a second. So let's do this. Let's think about it this way. So let's let a time just after t is equal to 2 be t is equal to 2 plus h. You know, like YH, it doesn't really matter. You could have used any other variable. Later you'll find that it does mean something. So then the average speed is going to be y at 2 minus y at 2 plus h. And you know what? Let's switch those, because 2 plus h is further, and that way it makes the numerator positive. Does it matter? Actually, no. Just like, you know, as Tony said a minute ago, it's slope. Does it matter which point you use first? No. It's all going to work out. So let's do t plus h, or excuse me, 2 plus h minus y at 2 over 2 plus h minus 2. So in terms of an equation, then this is going to be 16 times 2 plus h quantity squared minus 16 times 2 squared all over h. And what we're going to do on your calculator is we're going to put this equation in, and then we're going to look at, well, what sort of values do we have? So let's make this, and I don't know about you guys, but when I have something that's that ugly, I like using the horizontal fraction. So that's going to be 16 times 2 plus, and because your calculator only accepts certain variables, squared minus, what is it? That's 64, isn't it? We've already calculated that, all over x. Now, x is the elapsed time, right, after 2 seconds, yes? Okay, so I'm going to go to the table. Oh, hang on a second. First of all, I'm going to go to table setup. And I'm going to change the independent to ask. You may have never done this before. It's actually kind of cool. You can put in whatever number you want then. So now if I go to the table, there's nothing there. Okay? So I'm going to put in, just real quickly, -2, and you're like, why -2? Well, that was at 0. That's the 32 feet per second on average, right? So if I do 1, that means between time t is equal to 2 and time t is equal to 3. On that interval, the average speed is 80 feet per second. But that's an interval from 2 seconds to 3 seconds, right? That's a pretty good chunk of time for what we're looking at. What could I do to make this a better approximation for what we're going to get at 2? So this is the average from 2 to 3. What can I do to maybe get something closer to what's happening just at 2? Okay, so yeah, what if I called this 0.1 and did just from 2 to 2.1? Well, that's 65.6. So that's a much smaller time interval, right? Well, what if I did 0.01? I made it even smaller. No, 64.16. And what if, I don't know, let's make it 1/1000th. And you could get nuts with it and just, what do you think that's probably going to converge on? What numbers do these seem to be getting closer to? 64. I would imagine that I have tripped over. Yeah, and at that point, it can't keep track of enough decimals to do this. It says it is 64. If we wanted to do time a little bit before, we could do like -0.001. And it's 63.984. So it's getting close to 64 that way also. So the average speed as h goes to 0, then the average speed is, I'll go ahead and put that it's approximately, but I'm pretty convinced that it's exactly 64 feet per second. Now, to confirm this algebraically, I'm going to go ahead and expand that expression. So that's going to be 16 times 4 plus 4h plus h squared minus 64 all over h, which will be 64 minus 64h, excuse me, plus 64h, plus 16h squared minus 64 all over h. The 64s happily subtract away. We get 64h plus 16h squared over h. Notice if we substitute in 0, we still get 0 over 0, which is problematic for us, right? However, I can factor out an h of the numerator. And I get h times 64 plus h over h Now, I'm going to write this. I'm going to see if you believe me or not. Is that true all the time? Is that equal to 64 plus h all the time or not? Where's the one place where it's not? Where's the one place where these two are not exactly the same? When h is 0. Because when h is 0, this is undefined. But everywhere else it is. So when h gets close to 0, this agrees with my idea from earlier, that the average speed is 64 feet per second. All right, let's move along. All right, so you guys did limits last year, yes? All right, we're going to talk real quickly about what a limit is and what it is not. So when we say the limit as x approaches c of f of x is equal to L, what does that mean? Well, first of all, to be not completely formal about it, but be probably more formal than you did in pre-cal, f of x has to be defined everywhere in some open interval containing c, except possibly at c. Second, it means the value of f of x can be made as close to L as we want for x values sufficiently close to, but not equal to c. So here's the deal. When we're saying the limit as x approaches c of f of x is equal to L, we're saying that when x gets close to c, but not equal to c, the function gets close to L. What's the upshot of this? Although we'll use it a lot of times, we don't care what happens at c. If I cared about that, I would ask you, what is f of c? When we're doing the limit, we don't care what happens at c, we just care what happens near it. So, on all of these, the limit as x approaches c of f of x is equal to c. Because if you take some, you don't need to write this, but some little interval about this, if I get really close to x is c, the y value gets really close to L. Same thing is true here. If I take this, on that interval, if I'm close to, but not equal to c, I'm really close to L. Notice, is the value of f of c L? No, it's this point up here. And on this one, if I look anywhere inside of that small interval, if my x value is close to c, my y value gets closer and closer to L, even though f of c does not exist. So here, why is it that the limit as x approaches c of g of x is not equal to 1 here? And sometimes students protest about that. They go, well, is g of 3 equal to 1? Yes, it is. Because there's a point at x equals 3 where g is equal to 1. The problem is that if we do our little interval, if I get close to x is 3 on the left side, my y values are close to 1. But if I get close to x is equal to 3 from the right side, are my y values close to 1? No. So a function f of x has a limit, capital L, as x approaches c, if and only if. You may or may not remember from geometry, if and only if means it needs to go in both directions. If the right hand and left hand limits at c exist and are equal to c. So when we say the limit as x approaches c of f of x is L, we're saying both the left hand and the right hand limits as x approaches c of f of x are equal to L as well. Both sides have to agree. All right. So, polynomial, rational, and trig functions all have the property that the limit as x approaches c of f of x is equal to c, provided that f of c exists. Any place where those functions exist, the limit as x approaches c and f of c are the same thing, which is why we use that a lot of times to find a limit. It's just you can't use it all the time. The more interesting ones is where you can't use it. So, for some functions where f of c does not exist, we can estimate the limit as x approaches c of f of x by use of a table. So on this, use a table to estimate the limit as x approaches 0 of x over sine of x. So I'm going to grab my calculator again. I'm going to go to, I have to wake mine back up. Wake up. Seriously. There we go. I'm going to put in sine of x over x. Oh, one thing. For this class, we almost never use degrees. Everything's radians. Now, that's bad news for those of you who are taking physics, because in physics, almost everything is degrees. So make sure you're in radian mode. And I'm going to go to my table. I'm going to clear these out. Delete, 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 delete. So I want what happens near 0. And I want to look on both sides to make sure that they agree with each other. So I'm just going to pick something really close to 0. I'll do 1/10,000th. And it says it's equal to 1. It's not actually equal to 1. If you do 0.001, well, how far do I have to go before it doesn't give me 1? There we go. And I'm also going to check on the other side. So negative 0.001. It agrees. So the left and the right sides must agree. If they do not, that limit does not exist. So according to this table, the limit as x approaches 0 of x over sine of x is approximately 1. You can also get that by graphing it and tracing really, really close to 0. All right, according to my clock, bell should be ringing any second now. You do have an assignment tonight. It is in the textbook. So, come on, bells.